Hi. I hope you had a good break, maybe a short walk. It's a beautiful space. So I'm really honored to be here in San Francisco today. And my name is Lysandre Follet, and I'm the director of Generative Design at Nike, where we sit within the Innovation Design Studio. So 1968, Doug Engelbart and the group of 17 researchers working with him in the Augmentation Research Center at Stanford University presented a 90-minute live public demonstration called NLS. The NLS system was really the first to employ the practical use of mouse, textual information, and it was really a groundbreaking event. It's been called since then the mother of all demos, and people keep referring to it. What is interesting and that I want to pause on is at the time in Stanford, there was also a lab, emerging lab working on artificial intelligence, but what Doug group was really focusing on was augmenting intelligence. In 1962, Doug Engelbart said that a new tool doesn't just make something easier, it allows for new, previously impossible way of thinking, of living, of being. 1962. 1997, after a few years of research and development, IBM built Deep Blue, a state-of-the-art computer designed to run powerful algorithms to play chess against the best player in the world. And I think we all remember what happened in May 11, 1997. This big computer, Deep Blue, is set for an historic chess game with legendary chess player Garry Kasparov. On that day, something happened. Deep Blue beat the world chess champion after a 6-game match, 2 wins for IBM, 1 for the champion. But what a lot of less people know about is that following his defeat against Deep Blue, Garry Kasparov recognized the potential of such an advanced computer system, not just as a human versus computer setup, but as a partner in the game. That idea of partnering with the computer. Garry Kasparov developed a variant of chess called advanced chess, also sometimes referred as center chess, which is an interesting term. The objective was really to have a human player on a computer chess program playing as a team, that notion of team. So we're not trying to beat against the computer, but we're playing together to enhance the game. And many advanced chess players have stresses that playing as a team with a computer has merit in increasing the level of play to heights never before seen in chess, also producing blunder-free game with the qualities and the beauties of both perfect tactical play and highly meaningful strategic plans, and giving the viewing audience an insight into the thought processes of strong human chess player and strong chess computer. And note how early adopter that idea was back then in 97, we all recognize today the need for a more transparency learning experience, especially with artificial intelligence. On the same year, a couple of bright minds from Stanford launched Google. We all know what it is now, but at the time, it was that simple idea of indexing web pages with a ranking algorithm. At the time, press was talking about complicated mathematical analysis, and John Norton from The Observer in 1999 wrote about an ingenious algorithm. And that notion of algorithm is important and has evolved a lot over the years. And I always love that slide that shows it's a little bit outdated, but it really shows how from that simple search algorithm, the product has evolved with more and more feature, and in the recent year, a lot of intelligent feature. So that idea that piece of algorithm that run on that computer can get more and more powerful. In today's world, algorithm, artificial intelligence are everywhere in our pocket, driving our car. And like never before, our digital and physical world are really becoming linked, and it's transforming how we make and interact with things. What I'm interested to talk about today is how we can leverage those same very concepts that we just saw, powerful concept, and method to radically change the way we create product. Also, how those products are becoming more and more personalized. So at Nike, based in Oregon, founded in Oregon, from the beginning we've been maker, craftsman, thinker, and innovator. It's a mindset that really helps us push the boundary of what's possible and change the landscape of modern sport design. This is Bill Bowerman. In the late 1950s, Bill Bowerman was really dissatisfied with available running spikes. They were made of weighty leather on metal. And as a result, he really became obsessed with shaving an ounce of shoe to help runners slash second of their best time. So this quest really wound up redefining athletic footwear. And in the 1980s, we see here Bill Bowerman making custom shoe for his athlete by often using like really analog method. He will draw the outline of a feet. He will measure the width. He will note individualities from all his different athletes, such as an extended heel or slim ankle. So that idea of personalization, tuning an existing product to make it better and more personalized. Nike mission statement and vision is to bring inspiration and innovation to every athlete in the world, and not only for professional athletes, but all the athletes. And as Coach Bowerman will say, if you have a body, you're an athlete. So question we could ask is, how do we design for every athlete in the world? Well, it's really complicated because we all have a different body, and we really are dealing with a complex design problem right there. And for most of all of you, actually, you can check tonight before going to bed. You will most likely figure out that your left and right foot are even different. So how do we deal with that? I really like that visualization because it kind of gives a good idea of the beauty and diversity of body for very different sports and how the muscle group and the body adapt also to those different activities. And for the last few decades, as we design product, we have optimized against sample size. So what we call sample size is often size men's 10 or women's 8. And then we scale and modify as we go through the size. And that way, performance really isn't perfected. With traditional method, it kind of is as good as it can get. So in 2013, we started working with Jamaican Shelly Ann Fraser-Price sprinter. She's a really high-cadence power sprinter, one of the best female sprinters in the world. And the goal was to build for her the best performance spike for the 2016 Rio Olympic Games. And she really was a good test subject for our program because she was wearing a size 5 spike, which is really, really small feet. And we knew that we had a lot of performance issue with that product. So we spent a considerable amount of time to meet with athletes. We listened to them and really put them at the center of our design process. And using state-of-the-art equipment, we have taken the data from thousands of athletes in the last decade, from the best marathon athlete to someone that just started running. And here is how the sports science collect the data back on campus in Oregon.
If you take science and design by themselves, they have no power. They're not going to do beautiful things, but the overlap and the convergence of those two together, it's when beautiful things happen. It's an extremely creative process to be a researcher in the Nike Sport Research Lab. If you look at all of us, we're all extremely passionate about sport. We geek out on the science of athletes and athletic performance. Every day is a new challenge, and we want to make athletes better all the time. Athletes ask us for three things. They ask us to make me better, to protect me, and to inform me. The better you understand the needs of that athlete, the better you're going to make product. Motion capture is one of the tools we use. What it allows us to do is really objectively understand an athlete in motion. We use high-speed video. Most digital cameras capture around 30 frames a second. We can do 30,000 frames a second, so we can see things you don't necessarily see with the naked eye. Our force plates take thousands of measurements per second, and we get forces in three-dimensional space. We have environmental chambers. We can collect things like expired gases, so we know the amount of energy your body is using to do a particular movement. And in these chambers, we can accurately replicate weather from anywhere on the planet and make sure that our product is going to work in those environments.
So we have a lot of data, but with traditional method, it's often hard to make sense of it. So how do we best leverage data to inform design? Well, most of the creative software for the last decades have been replicating traditional processing, giving the experience of drafting, drawing, or sculpting. They translate how humans have traditionally been working with physical material. So at Nike, design has always been highly iterative, with ideas dreamed up, and evaluated, refined, or discarded on the way to the kind of innovation that define an industry. So as the athlete we serve continue to break barriers, we have to keep pace and we have to stay ahead, get smarter, faster, and better. So in 2012, we started to look at an emerging design method and process called generative design. And I always like to go back to the definition from Wikipedia that say that generative design is the application of computational strategy to the design process. And that the goal isn't to document the final results necessarily, but rather the step required to create that results. So where with traditional design, you will kind of like maybe sketch something and move into the process and have one or a couple of solutions. With generative design, what is interesting is you really want to document the step to create all the results that will be possible. So generative design really changed how the practice of design is expressed, from simple drawn geometry to a highly sophisticated algorithm-generated logic. It really is a revolution of problem solving. Generative design has been heavily used in the last decade by architects with pioneers such as Zaha Hadid, and it's now transforming a lot of industry from medical to car company. And those are often the three elements that you will find in a generative design process, which is a design schema, a means of creating variation, and a means of selecting desirable outcome. So let's unpack that a little bit. So step one, we saw that data collection is very important, and it is even more important in a generative design process, and we'll see later why. So in 2013, we brought Shellyan in the sports research lab in Portland, and by placing sensor in the shoe, we were able to track how much forces Shellyan apply on each stride. So once the researcher gathered that data and finished to analyze the data, we started to have a good understanding of what needed to happen to make a good hit performance target. What we really wanted to try to do is to be able to create a tunable sprint plate structure that will be as light as possible while maintaining an accurate control on localized stiffness. So the step two, which is maybe one of the most important steps in that generative design method, is translating design problems into computable parameters. Or we could rephrase it as saying translating the design problem into constraint in the generative objective. What we did is we look at nature for guidance, and we found this photosynthesizer. It's a planktonic diatoms. It's a microscopic organism that lives in the ocean and that solves this problem really well. It's very light, but it has a stiff shell. So this organism has evolved over millions of years to become one of the most performing systems in this group of phytoplankton. So the idea here is not to just take the aesthetic and bring it back to a product. It's really to look for the principle and architecture of that organism. And this is how we started to shape the design process by writing algorithms that will define how the design gets constructed. It is that interesting idea of building a tool versus using a tool. So we're not using an out-of-the-shelf tool. We're actually building our own tool, like maybe a lot of people were doing before in woodworking, where they will need a specific tool and they will build it for a specific purpose. So we're writing algorithm. And of course, it's like a digital tool. But it's a tool that, again, doesn't just make something easier, but allow for new, previously impossible way of thinking, creating, of making for us. So the step three is creating variation. Once we have a system in place, we can quickly generate massive amount of design. We can experiment with parameter, make adjustment to the algorithm, and introduce constraint. And the designer and the algorithm really start to work together to translate this understanding to create something extraordinary, a design never before seen with a mathematical simplicity. What next? This fluid geometry unlocks a fascinating kind of living intelligence, one that treats those patterns and structure not in a static spreadsheet, but as an active ecosystem. It's a constant moving system. It is then translated into a variable stiffness structure, similar to the one found on the diatoms. This structure can provide more support where more support is needed for each individual. It has a highly tunable ground contact traction and an optimized weight to stiffness ratio. The step 4 is a very exciting one for a creative person, which is exploring design space. So we talk about that idea that We don't create just one solution, but a non-finite number of solutions. And that's that idea that generative design offers a very different approach. We're leveraging dynamic system that we can interact with. So instead of creating, again, that static design, we build a dynamic system. Each time we run a loop of that algorithm, we generate thousands of solutions, building a design solution space, a non-finite space. Here we see a design exploration for a drone chassis by software company Autodesk, based in San Francisco. Actually, we'll recommend everybody to go check out their facility in San Francisco. It's pretty cool. They have a nice gallery. And what they're doing here is a multiple design solution they're exploring for that drone chassis. It gets optimized by the computer to find the best solution possible to the problem. It's endless possibility. We really see that we can unlock imagination. Step 5, of course, we now have that huge design space. We need to find a way to search and curate that design space. And we have a couple of different methods. One of the things that we do a lot is we leverage computer simulation to validate the design solution performance target. It's really fast, and it allowed us to quickly understand our design space. We can narrow down the design space, the search space, and remove all the solutions that will not meet the criteria. So here we see a bending stiffness test. All the solutions that will not pass that test get removed, and we start to understand which subset of the design space we need to focus on. The second thing we do is a lot of real-world testing. Leveraging 3D printing and additive method, we can drastically cut development time on expensive tooling and produce highly tunable performance footwear to test. This is Shellyan's first 3D printed prototype, grown and assembled in Portland, Oregon. In a matter of days, we can generate and build a new design, which before would have taken us maybe 1, 2, or potentially 3 months to send to Asia, have a mold made there on a part back. And by the time we will get the part, we had already moved to the next iteration. So now we're able to print them and assemble them overnight. We can test them on athlete fit, gather new data point, and feed that new data back in the system and rerun a design loop. It is a highly iterative design process. The role of the designer at this stage is to reframe subjective human preferences, such as comfort, performance criteria combined with aesthetic. Augmented by the computer, the designer really take on a role of curation. I like this one, but I think that plate performed better. This one is really ugly, and maybe this one is the one we want to go with. With generative design, we have solved one of our biggest problems, which is that idea of designing for the size. So here is 4 athletes. They all run the same distance, 100-meter sprint. They're all world-class athletes. The difference is they all have different shoe size. And remember, I told you that in history, we designed for size 10 and then scale up and down. What we did this time is going back to the algorithm, understand what are the performance targets for each size, and rerun a unique expression, a mutation of that algorithm, of that DNA. And this gave us multiple unique design, as you can see, the cell arrange and find the best configuration possible to meet the performance criteria. So this was really a groundbreaking idea and realization for us. And we didn't stop there. So again, 4 world-class athletes, and they're all running. The differences is they're running from 100 meters, so straight line, and then they start to take the curve around the stadium up to a 10K with Mofara. So we have here 4 different distances. So why not doing the same exercise? So based on the data, we knew what needed to be done in terms of performance for each product. And again, we mutated that algorithm and rerun specific solution. So as you go from running a straight line to taking the curve, the geometry gets tuned specifically to allow the medial to lateral flexion. And for the 10K, it gets as minimal as it can be based on the data providing where the traction and stiffness need to be. And this happened. After 3 years of hard work, we could have not dreamt of a better stage than Rio Olympic to validate on the track the performance of our product on the feet of most of the best athletes in the world, helping them achieve their dream. We had more than 45 medals in those new products. And what we decided to do after that success is looking across the business, and we say, well, we also have other category of product that are trying to solve that same kind of like performance criteria of having a light product with a very highly tuned control over stiffness. So we were able to leverage that very same algorithm to create solution across a category for American football, but also baseball. And what we have really done here is creating a family of performance products that all share that same DNA, that same algorithm that mutate to create those very specific individualized solution, but it is from that same roots. It's a family, a class of solution. And in this creative process, the computer generates thousands of design solutions that the designer on its own will have never envisioned, as well as many artifacts, creative artifacts along the way. Imagination is truly unlocked with surprise and delight. The computer becomes a partner in creation. It is co-creation. And it is that very same idea that Garry Kasparov had in '97 with Advent Chess, playing as a team. We are creating as a team. We are augmenting creativity, and this is what is really exciting for a creative practice. Machine and system are becoming more and more intelligent. There is a beautiful learning opportunity for the designer on the creative process. Today, I wanted to finish on a quote from Lysandre after playing against and being defeated by AlphaGo. AlphaGo showed us that moves humans may have thought are creative were actually conventional. I think this will bring a new paradigm to Go. Thank you.